And so let's do just a little quick introductions of the three of us here real quick. One second. There we go. All right. So who am I? I'm John Scholl. I'm a research scientist with ODU, but I work under a center called the Virginia Institute for Spaceflight and Autonomy.
I'm Patrick Ball. I'm the Associate Director of Operations at the Hampton Roads Biomedical Research Consortium, which is a consortium of Old Dominion University, Centera, Norfolk State University.
And last but not least, hello, my name is Hector Garcia, and I'm the Director of Collaboration Technologies at our research center here at ODU, the part of the Division of Research and Economic Development. And, I'm a big believer that innovation is not something that you keep in the lab space.
Right.
I think that the most powerful is when it empowers others to either discover or create or solve some meaningful problems, like some of the things that we're trying here. So hopefully the information that we present here can help a little bit, nudge a little bit in that direction.
That's right. All right. So let me go through a little overview. So most of the presentation we're doing today is about sort of 3D printing and additive manufacturing from our take, and then sort of how we've gone into the industry and sort of helping the aquaculture industry currently, and send some future pieces, as well as sort of how and why we've got Hampton Roads Biomedical here. I think there's some interesting stuff there. Patrick is right next door to a facility really located here, and we try to cross paths as many times as we can. And there's reasons behind it. There's a little bit of a method to the madness. I'm going to hit very lightly on some autonomous platforms we're using currently, just to sort of say, hey, these things are out there, be aware of them. It might not seem that far off, if that makes sense. And at the very end, there's some work actually that Virginia Sea Grant is currently funding me on that I've got to sort of get ready to show and tell in the year 2027. And so I'll talk a little bit about that. Right now, sort of internally, I'm calling that Blue Node. All right, so what is 3D printing? What is additive manufacturing, right? And so what are we doing with it? So if you're not familiar with this, think of 3D printing as sort of like we're building and slicing pieces of stuff that sort of is additively gained, right? So if you took a bunch of 2D pieces of paper and you cut out the same shape and you stacked it on top of itself and you kept stacking on top of itself, you would get this sort of three-dimensional shape, right? And so we use that here for so many things. Initially, when we first got into it here, it was really maybe for like one or two projects, or maybe there was an interest from a researcher or a project scientist here to say, hey, I'm kind of interested in this sort of application, or maybe even some of the theories that go into how these tools work. And really, fundamentally, I think it's important to understand that this sort of innovation really was from the DIY community, right? It literally was people taking apart old sort of traditional printers and using the components to pretty much make this sort of tech as it goes. And that's really how its roots kind of started. It really was sort of this very collaborative space where then researchers got involved and they started coming up with all sorts of really interesting mathematical equations to solve very difficult challenges that 3D printing as a now sort of tool that we have that's so easy to use now, before had its some sort of issues, right? So again, so why aquaculture? Again, very kind of grassroots, very DIY, very specific problems, right? Like how many times you're like, oh, I got to go run up to the hardware store and get this thing that I need to find, and you sort of piecemeal something to solve your problem. Well, really that's where I immediately now am thinking 3D printing is really it has a great location right there. Very customized solution that you need at a small scale, as well as there's ways to go large scale with it, right? So I talk about improving efficiencies and sort of reducing maintenance. I'm going to talk a lot more about that. So, all right, so again, why should this matter for farmers, especially within aquaculture? And I would actually argue a product kind of across the board in sort of agriculture, but let's just focus in on aquaculture. Again, this resilient piece, right? This history side of 3D printing, it really does sort of align to how the community is already solving its own problems. Every time I've talked with different farms, as they're sharing information or not sharing information, they're all sort of coming to various conclusions or what worked for them, and then another farm will take that and run with it. And really, that is sort of 3D printing. I can't tell you how many times I'm trying to print something and I might have a problem. I might ping Hector and say, hey, I'm trying to do this thing. And he's like, oh, this person had a similar issue X amount of years ago, and they found out this really great way to solve this. It sort of lends into citizen science side, right? Where you're using the community via social media or these other sort of forums to sort of, collectively come together to sort of help navigate or solve or give you some insight into information. And again, something that comes up a lot when I talk with groups is they don't think it's relevant, or they're like, I don't have the time, or I don't have the investment or the equipment, or I don't even know where to begin. And I would say, what's been really cool in the last maybe decade is that most of Virginia's, at least Virginia, most of the public schools now probably have either one school or all of the schools within, say, a district that has a sort of 3D printing lab, which means that there's equipment that they probably have right now that I can almost guarantee you is being underutilized by kids and faculty and support staff there that want to do fun things. So I would encourage everybody to really think about that and say, hey, maybe I do have this need or use case, but I don't want to spend $1,000 to get involved. Maybe I can just go down and talk to so and so. I know a teacher. Let me go figure out who the STEM coordinator is, right, with my local school. And I almost guarantee you that you'll get some eager kids just ready to jump in and help. Right. So I mentioned some of the costs there. So I would say today is probably the best time to sort of get in this space, because now there's products that are very good. They last for a long time. They might not be easy to repair. Some of them are easy to repair, but you might pay a little bit more money for them. But I would say you can probably get a pretty good, robust, single setup for you for easily under $1,000. I'd actually argue you're closer down about maybe about $500. And you can go cheaper, but you might get products that sort of don't hold up as well, or they're not as easy to repair, right? And so some of the stuff that I'm going to show today and the pictures you see here were all primarily designed in some 3D CAD software called Fusion, which there's certain free licenses you can use for like educational use cases. There's also open source software out there that I can gladly pass that information on that is completely free. Like Patrick will probably talk about Blender a little bit about that later on. And then you've got these sites. So I mentioned a company, Prusa. Prusa is a very popular company. They make these sort of really interesting 3D printers that they've kind of have a history of them where you can sort of come in at a very low cost entry model. And if you want to upgrade all the way through, you can, all the way going back 3 or 4 different generations of those printers. And then they host publicly for free, for almost free. Some people make some money here too. You go to a site called printables.com and you can basically just start searching for models. And you'd be surprised like how many little attachments that people make for like IKEA furniture. Or maybe you have like a workbench that's very, popular used across different industries. You'd be surprised to find that somebody's probably already made a little ring or something that lets you mount a hook to something without you even having to do any design work at all. You can literally download the file just like you downloaded a PDF, send it to your printer, and like magic, the thing will start working. So other ones in there too about Bamboo Labs and whatnot. I have a preference for Prusa. It's a personal preference. I don't want to pass on judgment to you guys, but I'll get in those fights if I have to. All right, so what this kind of then turns into is this sort of 3D printing mindset. This is what happened with me in my own story. So the moment I sort of turned this part of my brain on, I now just am like, oh, I can solve that problem with a 3D printer. Everything becomes this sort of 3D printing solution. And I don't think that's like a wrong way to approach it. I mean, so some things I probably shouldn't be doing this with, but like my argument is sort of like, why not? Before, I probably would have had to spend time and energy trying to sort of find some stuff out there, or maybe fabricate something out of some other material that just wasn't going to hold up, or it was too strong, like it was too much. I didn't need to go weld this thing and vice versa. So to me, it really is sort of empowering, right? And so what sort of happens when you start to get into this workflow is there's sort of a way in which you start to sort of attack a problem. One thing is to sort of, you really have to start to understand the space in which you're working in and sort of a 3D version of that. And you usually start in sort of 2D worlds. So you might start with like the measurement across the surface, across the top. And that measurement might give you some information about, where I need to put a clamp or something. And then you would go into your program and you would sort of draw it like traditional CAD, traditional drafting back in the day. And you can even sketch these things out now and actually scan it up to a computer and they'll turn it into CAD files for you, which is pretty wild. So generally it all starts as a 2D drawing. And I would argue anybody probably on this call can sketch something out. And I would actually say farmers are great at sketching out their problems. I've got this tool and I really wish I had something that was this shape. As soon as I hear that, I immediately think, oh yeah, we can solve this problem. We can probably print you something or print you a bunch of sets of parts that you can assemble in a certain way to go after that problem. And then there's this idea of like taking this 2-dimensional drawing and sort of then extruding it into the 3D space. And really like at the fundamentals, that's sort of it on the design side. You're just playing around with turning 2D shapes into 3D and then playing with sort of different operations like removing stuff or subtracting, taking away or adding to that. And then at that point, you sort of have the thing you need, and it's in a one software environment like a Word document. And now you want to sort of get it into a way to where it's easier to work with in a different software. So maybe we're familiar with like exporting to PDF, right? So in our case, we would bring that over to another piece of software, and we would get it ready to print. It's called a slicer. And then at that point, it gets basically converted to 3D sort of magic. And Patrick's going to talk a lot about those workflows later. But then it works for your printer to understand sort of how the print head needs to where it needs to go, how much material needs to pass through it, and do that. So I just want to sort of hint at that, because the moment you start going down this road, and I know this is what's going to happen with the farm that I'm going to talk about in a little bit here, because I think they're already starting to think like that. As soon as they saw what I was able to do pretty quickly, they were like, "Oh, well, hey, what else can we do?" And that's sort of where I think it's really important to go after. All right. So we do have to bring up plastic. I feel like it would be a disservice not to. So yes, we are introducing plastic into an environment that we already know from a research side is not great. But let's also then kind of flip that around. Let's say, hey, let's do it in a way to where we can try to be as the best practices as possible. So then you get into the material science of this, and I will upfront say I'm not, this is not my background, but I've done a lot of due diligence on PETG, which is a certain type of material. And then PETG is actually really good for sort of these environments where it holds up a lot longer than some of the other materials that are kind of out there that you sort of start with. One's called PLA. And so the reason we pick PETG is it usually has about a 3 to 5 year shelf life before it starts to break down. That means we put it out in the environment, as long as it's not getting sanded down, right? So we're going to put it in an environment where we're not trying to do that. The material will hold up. It won't fall apart. It won't actually biodegrade at that moment in time. And then we're trying to also make sure that our design that we're using for this particular problem I'm going to introduce is really also being supported by other tech like zip ties. So the idea is not to put something out there that's sort of free floating or free to go anywhere it wants to go. The idea is to sort of put it out there and enforce it to make sure we kind of know where it is. We can keep account of that. And then on top of that, using colors that are very bright and very not natural, right? And so part of that design is, so again, if something does go awry, you immediately sort of know it. It's not like, oh, I want to match the basket or the cage, so I'm going to use black. No, I want this thing to be like neon orange or neon green or bright red, because I want to see if it is failing and I want to see how it's failing, right? So these were design intentions on the material side that I definitely picked to do. And there are some other materials that actually hold up a little better, but the byproduct and how you make them is not great either. So it's sort of like a catch-22. You're you want to sort of find you want the best of all the worlds, but right now the materials science is not exactly there. The other reason why PETG is because it's easier to print. So most people that have a traditional 3D printer right now can use that material and immediately start sort of building solutions for I would say, a marine environment. It also doesn't have these byproduct gases that come off of the material like a product called ASA. ASA is probably stronger, and it's an engineered material to be in really harsh environments, full-blown UV light. And it's really designed to take impacts, not break down. So it's actually on the paper, if you're looking at what's the best material to use in this environment, it is ASA technically, but I would argue that it's not needed for the use cases that we're presenting. So why go down that road, right? Let's use the material. Let's take a step back. It's more accessible. It's not as bad, and it still holds up for the use case window. And most of our use case windows here in Virginia might be for 1 season. And people might be surprised and be like, oh, you're only going to use it for a season. Well, it's such a waste. Well, the flip side is it's very cheap to print these things. So it's sort of it's better than throwing away thousands of zip ties, right? Which nobody wants to talk about, but it does happen. And it's still cost effective to where you can replace the material as needed so it's not biodegrading into the environment, right? And it really is important. There's other ways you can also sort of go down the food safe way with PETG. There's tools and layers and applications you can apply to the material to help it even make it to where it's more consumer based if you needed to have that be part of a safety requirement. So, say for the FDA or something like that. But I do want to mention ASA. And in these pictures, what you're seeing here is some work I did with a student over at VIMS who actually just got his doctorate degree. So congrats for Matt, Dr. Leganke now. And we were doing some tests with ASA. So these the green and red items you see here, the ones at the top are with RFID tags embedded in them. So it's really cool is you can start to print these things and you can kind of pause the printer and you can do an action, like put a magnet in or put a little antenna, a little RFID tag inside, and then we can encase it. And we did that because for the research that Matt was looking to do, he wanted a solution that was cost effective and that basically a farm could do themselves. And so this is what he and I kind of came up with. And he went out and put, I don't know, I think a couple thousand of these in the field for his research study. And I think they only lost like a couple of them. We really tried to get the design thin, flat. We buffed up some of the material layering inside to make it so where the endpoints that were connected by zip tie were really strong, right? And so that's part of those design decisions that we kind of go with here. All right, so 3D printing and VIMs, that's sort of how this all got started. So a little diatribe here. COVID, like everybody else, came in, was like, I want to change what I'm doing. I'm spending all my time building software for a lot of virtual environments. And it just kind of, to me, wasn't going anywhere. And I really want to reevaluate how I can contribute better to my own backyard. And immediately was like, well, what's in my backyard? The Chesapeake Bay. Who's doing work in the Chesapeake Bay? VIMS, right? No brainer. So I cold emailed Dr. Jessica Smalls, and I want to give her a lot of credit because she connected me with, at the time, was a new hire, Dr. Bill Walton. Bill and I got going, and it just one thing led to another. And immediately I sort of sold him on these sort of ways of thinking about how we could come in and find sort of what I call like low-hanging fruit. And one of the things we found were some of these upwellers he had. And he had an issue on his research farm where the upwellers, they sit up in these tanks, and depending upon sort of the water rate that's coming through and sort of the size of the oyster, sometimes they can get a little off kilter. And so, one of the solutions is sort of put like a stone or a brick underneath. But again, that water level is changing. It's sort of going, because usually at this time, I think they're bringing in water from the bay, the upweller. And so you just have sort of different flow rates. And so again, like I'm looking at this and I go, man, it'd be really easy just to take a couple quick measurements. I could whip up sort of like, small, medium, large, print it in an evening, show up the next day, zip tie the sucker down, and put a little tag inside of it. So if you wanted to, while you're going around to check on the upwellers, to have a mental and digital note that you visited that upweller, we could at least go that far with it. And that's what we did. So I think I spent 2 hours on site with him. I took a bunch of measurements. Patrick will talk later about how there's other ways to do that. I did it traditionally. I came out with a tape measure and I had little calipers and stuff. And then, I got out there, was like, all right, this is my design. What do you think? And he was like, oh, this would be great. We took advantage of that. I think he had already had some holes in it. So I knew I could sort of zip tie it to the base of the upweller. And then I kind of give this arm that we could sort of clamp or attach any which way he wanted to the sort of rim of the larger shape. So as you're seeing that print there that we did for him. And again, so as soon as Bill saw this actually work within a 24-hour window, he was just like, okay, cool, right? Come with me. We're going to go visit a farm in the Gulf. And I was like, seriously? So immediately bought my waders, went down there, Cypress Point, right? Talking to Jody and Dewey, and I'm watching what they were doing. And immediately I got the bug, right? So I do want to give credit where credit is due. Like Dr. Smalls, Bill Walton got me in. They opened the door for me to sort of come in and start to play. And it was really important for me to sort of like make sure that people understand. Because I think everybody has their own story of how they get to the industry somehow. And this is sort of my story, is I sort of just was like trying to do more or different things in my own environment and just sort of honestly lucked my way into this. And now I'm just not looking back. All right, so the thing I really want to focus on the rest of my time here is we did a small presentation like this at VIMS in April for part of a Go Virginia small little planning grant. And some people were there from Steamboat Wharf Oyster Company, Callie and Thomas. And they were like, John, we saw what you did and we have a problem. We have like 600 of these cages, and these are hexagon cages from Flip Farm. Now, these are older generation, so credit where credit due is Flip Farm has solved this problem. They have a new version of this cage, does not have this problem anymore. This particular version, when it came out, I think it was sort of kind of geared for certain environments. Callie and Thomas had in a pretty rough environment, and they admit to that. And sort of the tops where this tube connects rips off. And it ripped off on something like 600 to 800 of their cages. Ooh. And so now they have all this material that just has this huge hole in the top, right? And so they were like, John, we've already addressed the problem with Flip Farm. We have gear out there, but we still want to like salvage this gear. And I think this is like a big sort of dilemma in this industry. And there's other ways, there's a whole lot of material science. There's like other ways of recycling and all this stuff out there. And like, if I had all the time in the world, I think I would spend a lot of time there. But I just, I don't. And so I'm looking at this problem and I go, yeah, I think I could maybe come up with something. And then they showed me what they were doing. They were taking sections of, so it's taking basically two halves of this cage, cutting off a sort of like temporary patch, and then getting really creative with like zip tie weaving this thing together, where it was really strong. It was working, but it was taking them like 30 or 40 minutes per basket. And I mean, I don't know how many zip ties. They were using a lot of zip ties, but it got us sort of talking and thinking. And we kind of came up with this idea of like, what if we had like a little teeth thing, a little thing that could kind of grip, where you put the pieces together as like a sandwich, and then this thing sort of clamps in and keeps it together. And so initially, when I was thinking about it, I was thinking about something where we 3D print it, and it's sort of like a clip design where when you snap it together, it sort of locks in place, and it's pretty much impossible to get out, right? You almost have to break it to get it out. And then, you start thinking about the environment, and you're like, wait a second, we can't be putting stuff in there that the whole purpose is then, for it to break, to be, not working. So then I was like, all right, well, let's use, they're using zip ties, and let's make it fast. So basically generated a little channel inside one of our prints in our design that let us sort of go through that quickly, right? So you're seeing some pictures of like version 1 of 4 that I came up with. So the one on the top left there is where we took these 2 big pieces, we put them on the sides, we got 3 zip ties on each ones, and there's a channel in there, so it perfectly slides through. So literally from the user's perspective, you put the thing on the bottom, you shove a zip tie, it goes in one end, pops right out the other end, ready for you to quickly zip it in. So very quick to put together. But I still wasn't happy because these pieces were large and it took a little longer to print. And I also know that in this environment, you might have different sort of breaks, right? And these bigger pieces were only really going to work for sort of this version. So again, went back, shrunk the size down a little bit. So I would say all in all, after all the prototypes, I spent maybe 6 hours tinkering around with this stuff. I probably could have done it for a lot less in time. And we're able to pretty much put out about 12 to 16 parts, which ends up, I think, being something like 8 kits per print bed and about 6 hours of printing. And so then, like you see behind me, there's a bunch of other printers in my office. We sort of have like a print farm here. And so in the course of, a day, we could start pushing out, 4 kits per printer, right? Which is, 8. So 20 to 30 pages, hypothetically, half sides per printer, and then times it by 5 or 6. All of a sudden, 3 days of doing this, and I go, hey, I think I have enough parts for, 80 to 100 cages, right? And she immediately sent me a video saying, hey, it'd be great if, these curved ones are working great, but the big flat ones are just a little too big. It'd be great if we got them smaller, right? Oh, so let me go back, sorry. And so the smaller ones you'll see in the top right of that picture. So I don't know if you could see it, but basically just a little quick print, and the zip tie goes in one end, pops out the other end, right? So again, so I just wanted to highlight their use case because I feel like there's a lot of use cases like this. And Callie and Thomas were very open. They said, hey, this is the gear we have. This is the problem we ran into. If there's a way we could salvage this, we would much rather do that than sort of, throw this stuff away, right? They already felt like it was sort of a waste and, they wanted to see some good come out of it. So yeah, all right. So I'm going to kick it over to Patrick to talk a lot more about how we can do this in a much more scientific way.
Hey, everybody. Good afternoon. I'm Patrick Ball. Like I said before, I'm Director of Operations for the Hampton Roads Biomedical Research Consortium, HRBRC. One of the things I do is I oversee our prototyping and integration lab. So I'm just going to say up front that I'm not a shellfish expert or even a shellfish. Like, I don't know anything about shellfish, honestly. My areas of expertise are project management and additive and advanced manufacturing. So that includes 3D scanning, which I'm going to talk about, digital modeling, 3D printing, which John has been talking about, and just like the general process of taking an idea or even like an actual physical object and turning it into something that can be studied, something that can be tested, and then obviously something that can be used to solve problems, like real problems. So I just want to spend a few minutes showing what the process looks like and how we could support that kind of work in aquaculture. So you see on the slide there that we are the HRBRC. I'm not going to read the slide to you, but we're a regional partnership that brings together universities, healthcare organizations, industry, educators, and community partners. So a lot of my role is helping connect people who have problems with the expertise and the technology that can address those problems. So at the HRBRC, our prototyping and integration lab supports projects from just early idea stage through the physical production of a solution. That can include the 3D scanning, modifying, creating models, choosing the correct materials, a lot like what John was talking about with PETG or polyethylene phthalate glycol. I just want to sound smart.
Yeah, I didn't want to try it.
3D printing, post-processing, because once you 3D print a thing, the job isn't done. Is my microphone? Yeah, I'm good. And then obviously the iteration part is very important. So just the revising the design based on what we learn from the manufacturer. So most of the work we do is for biomedical prototyping. So you see up there, there's a baby. We produced a silicon baby that has 3D printed parts inside that you can actually perform medical procedures on. That particular one is for performing a lumbar puncture on an infant. And it works. It has, you can actually aspirate fluid from the spine. So these images just kind of show those anatomical models, but we also work with NOAA and NGS for just like little solutions, things to put on their tripod to put specific equipment in for several of their missions. Um, we also do things like, I don't know if I don't have any pictures on that slide, but like you can see here, museum kind of objects. This is the skull of a Homo habilis woman, for digital archaeology. And I just 3D printing is like the most visible part of the process, but it's just one step of this workflow that I think is applicable to a lot of industries, including aquaculture. And the first step is understanding like what the problem is, what the requirements are, and then you can begin how to address that problem. So if we can move to the next slide. Oh yeah, there we were already on it. Nice. So if you just start at the top left there, you can see that what we start with is the actual object. That's a real oyster that we got from Bill. Um, I always tell my students that, one way to get a digital model is to build it from scratch. Use a program like blender.org and build it. The far better way to get a 3D model is to steal it, right? So you can steal it online on one of those websites like Thingiverse or Sketchfab or Squidoo or 3dmodels.com. That's one way to steal it. The way that we prefer to steal 3D models is from real life. So we use something called a structured white light 3D scanner that picks up like the measurements and the actually the surface color, all these surface features of an actual object. What's really cool about it is like once you have that digital model of the thing, you can then measure it in a very meaningful way, in a way that would be difficult to measure it on an object that's not digital, right? So it's easy to go ahead and stretch across and go, okay, yeah, this is a foot across. But on something like an oyster, which is the example that we have up here, it's, like, what if you wanted to study the distance between ridges, right? Well, I mean, you can do that with calipers, or you can scan it and have all those measurements in one place. It's just a lot easier to do.
Hey,
So,
Patrick,
yeah,
would you consider like an iPhone scanner probably capable enough nowadays to do some of this stuff?
yeah, absolutely. So that's the kind of the thing. We have this fancy scanner, and you see a picture of it there on the slide, and I think it cost like $20,000 when we got it and it came out. But that is not necessary, and it's already out of date. And a matter of fact, if you have an iPhone with LiDAR, it can actually do, in my opinion, a better job than that giant scanner. So I don't recommend people go out and buy the most expensive scanner. So that's a really good point. We have one, but if you're just doing this at the farm or at your house or any place where you're trying to solve problems on the cheap, yeah, there are apps just for regular cell phones that do a pretty good job and can kind of capture those metrics. Now, if measurement is very, very important to you, you might want to invest in a more accurate kind of scanner that is geared toward metrology. But yeah, so once we actually have that digital model, we can measure it, we can change the scale, we can compare it with other models or other oyster shells. We can isolate specific features, modify it, add or remove barnacles, for instance, for any particular purpose. We can also send the model electronically to someone. I can send it to John, and now he has the exact same oyster that I have, right? For research or education, and you don't actually need to have oysters that can go bad or move an actual physical specimen when you have that digital model. It kind of opens up a whole bunch of avenues for problem solving. So once we actually have that scan, it actually takes quite a bit of work to turn it into a model that can be used. So we have to decide how large it can be. Sometimes there's like parts of it missing from the scan data. So there's like some post work there between the scan and the digital model that you can actually use. So where are we on the slide? Let me look at the slide. Oh, I'm looking at John. Are we still sharing the screen, or did
Yeah,
I?
you're still up there. It's still up there.
Oh, okay. Oh, there it is. Got it. So where am I?
Manufacturing, maybe?
Yeah, yeah. So once we have that digital model, we actually start thinking about how we're going to manufacture it. That means choosing the 3D printing technology. What John has been talking about is called fused deposition modeling, or FDM, but that's just one technology. There's also stereolithography, material jetting, and they all have different kind of implications, and they use different materials. Like John was talking about thermoplastics and recyclable materials, but there's also printing that use thermoset materials and non-recyclable like photopolymer resins and things like that. So we have to decide what kind of technology we're going to use, how we're going to orient that print so the layers make sense for the kind of strength that we're trying to get, and then we print it. So you can see here this printed 3D oyster. If you look on the right hand side of the screen, it's a direct reproduction of the shell that we had. We took an oyster, we scanned it, and we made a direct one-from-one digital twin and then a physical twin, but that's only like one option. You can also change it, make it bigger. Like I said, isolate parts of it. You can incorporate it into a different fixture or some kind of different setup. You can use it to create a mold to do some more like traditional manufacturing. Once the thing is printed, you have to all 3D printing requires some kind of post-processing work, right? So removal of support material, cleaning, apply finishing is needed. In the case of the oysters, and I have one in my hand here, we just put like kind of a clear coat on it to make it look real. This is a 3D printed oyster. This one has a barnacle on it, which is kind of neat. Let me know if you can't see it. Um, the most important step after all of that, though, is to me is evaluation, right? So you take the thing that you've made and you put it in the hands of the people who ask for it and say, well, how does it work? And you give them time to test it and then feedback. And I think like a lot of design, it's iteration that's important, right? So what we really do is iterative prototyping, right? We put the result back in front of the people who understand the subject and say, like, is this what you were looking for? Is this useful? Like I make medical training models, but I'm not a doctor. I'm not a surgeon. I'm not a medical person at all. I'm a prototyper, right? So I think for aquaculture, the value of this workflow kind of depends on the specific need, but it could support research by providing consistent like physical models for comparison or testing.
Hmm.
It can help with design of small custom tools or mounts or sensor housing or fixtures. And obviously, it can also support education, right? I can take this oyster and I can put it in a kid's hands. I can ship it to a teacher. It'll never go bad, and it's
Yeah.
accurate enough that they can look at it and kind of learn something from it. So I'm not suggesting that like every aquaculture problem needs a 3D printed solution, although when all you have is a hammer, everything looks like a nail. I do try to apply 3D printing to almost every problem in my life. Parts of my house are 3D printed. But like in many cases, 3D printing is not actually the right answer. But I think it's important to analyze the problem at hand and see if, yeah, maybe some additive manufacturing could quickly and cheaply solve problems. And that's across a ton of different industries. But I think specifically applicable to aquaculture in a meaningful way. So I think my main takeaway is that like 3D printing is not just a 3D printer. It's a whole workflow of problem solving. It's a way to move between a physical object or a real problem to a digital model to a tangible thing, right? And then iterate based on what you learn. The same workflow can be applied across like what we do, biomedicine, engineering, education, and aquaculture.
Yeah.
So that's
Yeah, no, look, it was
yeah.
great. We brought a bag of these up to Maine when we did a trip to Maine, and we had a lot of fun kind of poking around and messing with other farms. And it was great. We actually had a group that was eyeing it the whole time. And Patrick was like, "Hey, do you want to try it?" And they're like, "Where are these from?" Like they were trying to figure out which farm they came from. We're like, "Well, they're from Virginia," and they're like, "Wait, they can't be good." And then they held them, and then they kind of held them and they looked at them and they go, "Wait a second, what am I? What is this?" So
It's
it was just, yeah,
it's
it was really
accurate in the
cool.
way that it looks, but it's also accurate in like the material property and the way it sounds.
Feels.
I'm gonna drop it on the table in front of my microphone so you can kind of hear. Like it
I
sounds like
don't
an
know if it did it.
oyster
Yeah,
hitting the. Can you
it's
sound it?
it's probably getting filtered.
Ah, well.
Yeah,
Anyways,
it's
just
it's
believe me.
all right, cool. Well, thanks, man. I'm gonna kick it over to Hector here.
Thank you, John. So, we've been looking at a lot of examples of additive manufacturing being used. So I wanted to take the chance and think a little bit about how additive manufacturing could be part of the future of, agriculture, um, and how it can empower you to solve those meaningful problems at the local level, because everybody has different types of challenges that they need to address. Um, so I'm going to go through some uh, generic concepts for how it could be utilized and give you a few examples.
Hector, just let me know
So
when you need me to slide advance, okay?
yeah, no problem. So in this particular slide that we're in here, it's primarily focusing on tailoring habitats. John showed an example of making sure that you can work with your farm gear, right? Uh, the specific conditions of the site, etc. So you could think of additive manufacturing as a way to explore custom habitats. Right. So there's some examples here of how they've used additive manufacturing to create reef modules. And this improve larval settlement, water flow, and then the organisms start, growing and uh, inside that custom habitat. Um, John showed a very good example of this grow out equipment, circumstance where you have a lot of equipment, but you can't use it. And you could take advantage of that equipment in your farm without incurring significantly additional expenses. So additive manufacturing can come and help, fill in that gap. Okay, go to the next one.
You're
So,
good. Yep.
yep. So this is another, kind of thinking venue that you can look at for additive manufacturing. So you can look at it as a way for you to deploy smart sensors that will help you better understand what's going on at your farm, right? So all of these plastics, as John mentioned, they have enough resilience built into the material that you can very easily deploy it. It can be customized and deployed. So you can have all of these sensors that show you imagery, some chemical compositions, maybe even the health of your stock as it grows throughout, a period of time. There's other options that have to do with materials that actually degrade. So we covered something in here with material that we didn't want to degrade because they were plastic and you didn't want to add plastic to the environment. But additive manufacturing is not exclusively with plastics. There are other systems and machines that can use different biodegradable materials, right? So here, there's another example of an actual biodegradable leather that has been printed. There's a guy there. So it's a little purse, but this purse, if it's exposed to certain environmental conditions, then starts breaking down and it goes back into the environment. So this got me thinking about, a lot of the growing cycles for shellfish aquaculture. They start in bags, and there's one bag if there's one size, and then you have to change it, move them to different size bags. And, you know, uh, something that could be neat is if you have these biodegradable collectors and you create like a Russian doll analogy where you have all these little bags inside a bigger bag, inside an even bigger bag. They all have different biodegradable timelines. So as your stock grows, you don't have to remove it and spread it out into other bags. So the collectors kind of adjust as the time passes, right? So something that uh, additive manufacturing can allow you to explore, yeah, and see how it could help you, solve some problems. Thank you, John. So other parts is, you can use AI to look at specific designs, right? Uh, this is more for like entire uh, equipment components, right? So I didn't have here an example of a cage, but I have here an example of some structural element. So it has to have some strength requirements. And on the very left, you can see that that's the current production, but then you see different iterations as how you can maintain the durability and the mechanical properties, but then allow for savings in material. And besides that, you can even add other features or capabilities that were not present in the original design, right? And these designs to the right of the original one were not created by a human, right? You put in the set of your requirements and parameters of your goals, and then the computer starts iterating, many times, and then it comes and uh, collects the most likely designs that will fulfill your needs. So those are some examples in there. So this could work for having better equipment, better designs that improve the geometry for like water flow, strength, etc. Um, Other possibilities have to do with shell waste. So you could use the shell waste that is currently produced and use that as a material input for other things. So the example I have here is an air purifier that is actually created doing additive manufacturing, but the source material are oyster shells. So they crush them and they bring them back as material to create this air purifier. But you can think that how you could reuse some of that material that anyway is discarded and use it in different possible ways into your own system. Can we go to the next one? So here is some of examples that John was talking about, that they are marine grade, so you can have something that works well in the environment with the different exposures to the salinity, UV, all that stuff, and even underwater. So you can see here some examples of components that were customized to live in underwater conditions to collect and inform, the conditions of that environment over time, and up to an actual 3D printed boat. So you can look at we've covered 3D printing on small components that are part of your system, but you can go even to I can look into creating my custom boat that's specifically tuned for the task that I'm intending to do at the site, right? So you're not tethered anymore with just coming up with adapted components to the current platform. You can think of it, I'm just creating a whole new platform that works even better. Can we go to the next one? So other things to think about is the actual structures and the complexity of structures that you can design with additive manufacturing could also help distribute how the organisms grow and how you keep some of that, flow of nutrients into those cavities. So you could rethink the housing. Basically, you could look at using AI, design some knowledge of how the oyster grows, attaches, and maybe come up with some sophisticated designs that solve for a few problems that exist currently in the system. And because it's additive manufacturing, you can basically distribute the production of the solutions that you come up to other members in your community. So John was talking about, DIY community and how because of the cost and the ease of use and availability, you can basically distribute and get them closer to the farms. So um, basically, what it comes down to is to shape the future that you're looking for, right? We can print it. So here are just some of the summation of state of the art of rapid prototyping at the moment, right? So you have custom parts, reverse engineering, a small batch production. So we've seen that in the examples earlier. Um, Within a year time frame, the basic improvements have to do with speed. So a lot of these things that are printed, John was talking about, overnight turnaround is going to come down to, in the next 5-minute turnaround using faster hardware, AI assisted design, improved materials. But beyond that, you can start looking at integrating um, this digital manufacturing ecosystem with AI, robotics, advanced materials, bioprinting. Um, so smart advanced materials contain these 4D materials. So basically, it's materials that, when subjected to some external change, it can reshape or change the function of something. So there are some examples here in the slides. Bottom left, this is a 3D printed claw. And all we had to do was change the voltage range. It goes from fully open to fully closed, and it actually can close with strength. So it can pick up an object that is heavier than itself. So to the right, you can see an example where you have like custom sensors, but all the circuitry that goes into the programmable components and other things uh, in that 3D manufactured custom device also included the electronic paths, right? The circuitry that connects all of that. So these advances, are going to start becoming more common in additive manufacturing. So you're not just having one material. Multi-material is something that is currently available, but you can think of it as multi-material that alters function in whatever you come up with. So just a few ideas for you guys to think about as this technology is rapidly evolving, and there's always, different ways to adapt it to solve, some meaningful problems.
Awesome.
Back
Thank
to
you,
you, John.
Hector. Yeah,
Mhm.
I'm going to kick it over. We'll wrap this up quick here. All right. So for the most part, we've just hit on a lot of 3D concepts and pieces and things that we're using, things that we're looking to for the future. I'm really interested in sort of where you can print and do circuitry. There's some stuff that MIT is doing right now that's showing that it's actually going to be pretty cheap, where you can do like a whole linear motor. Maybe the size isn't as big as you would need it in sort of the industry right now, but it's just a matter of time. Once those problems are solved, then it's just a scaling problem. And so what I want to hit on just as we end here is there's also some other things that I think it's important to sort of introduce and talk about. There's some autonomous system work that's happening at ODU and actually all the universities. Virginia Tech's doing a lot of work here. They've been doing a lot of work for years. In all honesty, I have to give credit where credit is due. And we're using a platform you can purchase right now. It's called a BlueBoat. You can look this up. This is probably primarily why I wanted to bring this up. Its primarily use case is more or less still sort of on the researchy side to sort of play around and get familiar with the platform, where you can kind of build your own customizations for it. But long story short, you basically can program this thing to go around a GPS, right? It'll drive around and it maybe would do something of interest. So maybe it could do water sample collection. Our current setup, we have side scanning sonar on it, so we can go around and do sonars. And sometimes for some of the farms, they like to you look at that information to see like if the bottom of this area is going to be of interest. And traditionally this would be really expensive to do. You have to hire a firm and come on out. And what this company is trying to do is sort of bring that bar down. So this boat out the gate I think is about $5,000. You throw the scanner on and it gets closer to about $12,000 or $13,000. But from our perspective as like an institute, it's great because now I see this as an opportunity where the bar has been lowered enough to where I can come in, I can start to then learn how these systems work and sort of see where the future's going to then sort of have these conversations with you all. So I just wanted to bring that up. So something to look up, BlueBoat. And it's a picture of a little Bill. We went out to the farm and went ahead and had it sent it off. So I don't know if this is going to play very well or not. Probably not. Bill was
It's
really
playing.
concerned. Yeah, he was
Yeah,
concerned, like, is it going? Do I have it? Who's got control of this thing? And then it sort of all of a sudden it kicks in and hopefully it goes.
yeah,
Uh,
there, it's going.
Oh, that's so cool.
yeah. And so then we had to do a site survey of his farm just to showcase what you could do. While at the same time, some of the research people here are working on better navigation systems to do sort of a like, hey, there's something in my way, I should keep going, right? And surprisingly, water-based navigation way easier than roads. So I would say self-driving boats should be before self-driving cars. Just my 2 cents. All right, and then to wrap it up, just as something to put on your all's radar, because I look forward to coming back maybe this time next year. So part of a program project that I'm on, and we call it the Angry Birds Project, is we're doing bird detection. And so to try to figure out sort of how bad is it around floating cage gear, we're going to put a system out of VIMS to try it with the purpose of completely opening that solution up to the wider audience, for them to adapt it, for them to modify it, for them to hack it, do whatever they want with it. And long story short, we're going to have a box that has compute on board. It has a mesh network on board. So it's looking for a wireless signal. We're not going to put a SAT or SIM card in it because we want this thing to be sort of free if you have internet. That mesh network will piggyback. So say you're 1,000 yards offshore, say you're 5 kilometers offshore. We can actually go at about kilometer intervals and put a node for less than $100. And that node then piggybacks, right? So kind of like how your smart lights might work in your house. That way to say we can put the system out in the middle of nowhere. It'll charge itself, have a camera, a lot of interest in having surveillance on your equipment and gear. In our case, we're going to train that system to basically do some bird detection and maybe play some certain sounds and frequencies that they don't like, right? It's not that it hurts them, it's just don't like it as much, right? They're like, it's kind of noisy, I need to get out of here. So I'm going to put that on the radar, just to be aware of that. That's something that we're working on. We'll have some pretty cool stuff, I think, by end of this year, early next year. All right, so big thank you to you guys for this. So we've gone a little over, but it's okay. We still got plenty of time for questions. And I've got some links at the end here. Just want to, say thank you to all the participating parties. Really big thank you to Caleb Ralph over at HRBRC. He did a lot of that work with oyster scanning. And then the printing farm that Hector's got here at the center that I was able to come in and sort of take over for a few nights to pump out, a couple hundred parts. As always, Dr. Bill Walton, Dr. Jessica Whitehead with ICAR, had a lot of great conversations with her, and Callie and Thomas over at Steamboat Oyster Company, as they've been very, very open about their problems and just let me tinker and have fun. I'll be seeing them on Thursday, actually, to bring them up updated parts. All right, so with that, I will leave it, and I'll at least leave this screen up. You can scan that QR code, and that will bring you to the printables.com site, where you can download these files right now if you wanted to, or if you wanted to send them to somebody just to say you did it, right? And they're designed for the 6mm flip farm hexagon system. I think it'll work on the newer versions, but I don't think you'll need them, in all honesty. I think the new versions solved the problem that they ran into. But anyways, thank you guys. Thanks, Madeline.
Thank you so much. This was so informative and thorough, which I really appreciate, because as someone who doesn't know a lot about aquaculture and the manufacturing side of it, just in general, this was so helpful and super, super interesting. So thank you guys so much. Is there any questions? We have about 6 minutes, so you can either write them in the chat and I can read them, or you can take your mic off mute. I also do have a question, just in kind of anecdotal. But was there
Sure.
something that sparked your need for 3D printing, or was it just something that you kind of saw a need for? Like, was there any event that made you think this could really be useful?
Yeah. I think everybody sort of has their own moment where they come to it. I actually had a background working in restaurants for a long time in the service industry, doing bar management. And I did a lot of self-promotion material. And so I got into what's called vector drawing. So it's where you're basically using line art to do things like build flyers, menus, and things. And once you go down that road, you realize that it's all sort of combined. So I could actually take a vector drawing and then make it into 3D. And so immediately I was like, oh, this is really cool. And then, I forgot how, but I think I was a graduate student and we had just gotten in one of the new MakerBots. So MakerBot was this big company. They took all this work from the community and they basically put a product out, and it sort of overnight, blew the lid off of the industry, right? Everybody's like, oh, MakerBot, MakerBot. Now, unfortunately, I think as a company, they're not doing too great these days. However, they really were a pioneer there. And they were the ones that I got in. So it was immediately like, wait, I can just go print my own? This is crazy. What is happening right now? To me, it was just very eye-opening that, being somebody who likes to solve problems, and I have a tool that, I think Patrick said, everything I just want to hit it with.
It's pretty
Yeah.
fantastic. A buddy of mine just gave me a 3D printer one day because he bought it and he couldn't figure out how to use it. And he was like, "Here, take this thing away from me." And it was a cheap kind of Chinese reproduction model. And I recommend if you're going to get into 3D printing, get the worst 3D printer you can get, because fixing it is what teaches you everything about 3D printing. If I'd have started with a
Mhm.
Prusa, I wouldn't know anything today
So
because they're so easy to use.
for people that don't have a lot of time, I would suggest a Prusa, but build it
Yeah, it's
yourself.
better.
Build it yourself. Okay.
Yes.
You can learn a lot by building it yourself. It will take you half a day, but you will feel empowered when you turn this thing on and it just works. You're just like, I built this thing. This is crazy.
And it's not that complicated. If you've ever used a
No,
CNC
it's
machine or even seen one, it's the same concept, right? There's a couple of pathways, a few axes that it has to spit out some plastic. It's not that hard. But a bracket in my fridge broke. It was like a $50 bracket in my Frigidaire fridge to hold a shelf. And I was like, wait a second, I could just 3D print this thing. So I modeled it for free in Blender and then 3D printed it for a nickel. I did the material calculation. It was a nickel's worth of plastic. It worked until we got rid of that refrigerator. So that's kind of what made me fall in love with it.
That's
Yeah.
awesome.
So, yeah.
there was a question in the chat about some of the I think repurposing of the shell sector, and this is something actually it's relatively new to me. And I think
Mhm.
what's happening right now is in sort of like FEMA world, sort of where some disaster strikes, they're looking at reevaluating sort of structures that can be sort of built quickly. And there's some companies that are trying to sort of get their foothold into manufacturing homes and home structures out of sort of concrete that they've specially tuned to go through the same sort of systems. And they're just really big devices. And so my guess is that it's not accessible. I think right now it's more or less understanding the materials of the various shells and seeing how they differ to then come up with the sort of approach to getting that into sort of like a concrete mix. Once you get there, my guess is you could use any sort of printer that's been modified with a larger nozzle for that sort of work, and that would work. But it would be a much larger device. So just everything just gets larger. So your motors are larger, your axes arms are larger, your belts are larger. But fundamentally, the same concepts hold true, if that makes sense. I hope that answers that question.
Yeah, and just so that this composite, I'm putting the link on the chat. This is that composite for 3D printing, um, and it tells you about the composition of that material, all the different parts for the composition, and you have to use biomaterial type of um, 3D printers. You cannot use the plastic printing in 3D
Yeah.
printers.
And
So,
what you'll find too with a lot of these is a lot of them don't really have to apply heat. They're more about nozzle and flow rate control, and then the material properties, so it doesn't just come out as water, right? So like
mhm.
when you watch these concrete ones, it's really just two big motors moving this head around as sort of a controlled amount of concrete is coming out in a basically like an old school CNC approach where the machine head's moving around and this concrete's just flowing out at a rate that sort of aligns to the material properties. So again, it doesn't just turn into goo. And in some of those cases, they maybe are applying heat. Like I've seen there's been a bunch of work, material groups out of MIT doing glass printing, which is just this whole other world of material stuff that's really wild when you go down that road in terms of thermal dynamics. But anyways, so yeah, these things are out there. And I think in the next decade or so, I'm really hoping that they become more prevalent. Like it just becomes sort of like the DeWalt gear. Like, oh yeah, I've got my 10 by 10 foot system where I can, just pump through, I don't know, concrete, shell mix, whatever. And I can sort of,
Mhm.
build my own structures to then use as anchors or end caps for my dock or whatever. I mean, that's sort of what I would love to see happen. And so I think the push that I'm trying to push through like with some of the farmers is like don't like use me as a channel, use us as a channel to sort of ask those questions. Let's go after funding together to look at those problems if there's a need there, right? Because
Correct.
I don't think that's a difficult problem. I think that's just getting the right group of people together, and I think it's an integration problem, if that makes sense.
And also, if I'm sorry,
Mhm.
um, I'm also adding here because once it's in a powder mode, you can add it to other things. So there's even PLA filaments that have
Wow,
crushed oysters in it. So I put it there on the. Um,
awesome. Matt, what was the other questions you had real quick? I know we're about out of time.
I was just asking if we had one last question before we say thank you and end, but if anybody doesn't have any questions, then we can say thank you and be on our way. Are we all good?
Thanks guys for joining.
Yeah.
Thank you
yeah,
so
thank
much
you.
for including us. I appreciate being here.